Hey, hello everyone. We're going to finish off in this lecture what we started on Monday. So just talking about statistical inference, testing, confidence intervals, and now we're talking about sample size calculations. We did it with respect to the confidence interval, so how to choose a sample size to have the size of a confidence interval, or half that, the margin of error that you desire. Now we're going to talk about, in the context of testing, how to do sample size, and that's often the way sample size calculations are done, particularly in grants. So these are the three things that have to be stuck in to a sample size calculation. First, have to define the significance level. Again, that's the type 1 error rate, which is the probability of rejecting the null when the null is true. And that's usually set to be a small number like 0.05, right? And that'll affect part of the calculation. The effect size, so in order to do a sample size calculation, you have to propose an alternative. And usually that alternative is chosen to be kind of the minimum departure from the null that you'd be interested in. So maybe it's 5 or 10 or whatever it is. But you can't calculate a desired sample size unless you know how big the effect's going to be, so how big the departure from the null. And finally, you have to define your power, which is defined as this quantity here, and that is the probability of rejecting the null if, in fact, your HA, which you defined here, whatever that effect size is true. So you can think, if we go back, we have test is based on a test statistic. So we have a Z, which is our average minus our null value over the standard deviation of x bar. And again, ST of x bar is defined as the standard deviation of just the x itself divided by the square root of sample size, so of n. So sigma is defined as xd of x. Important to distinguish between these two. One is the standard deviation of the average of random variables, and the other is just the standard deviation of the random variable originally. So here's our test statistic here. And sample size calculations in testing are based on trying to achieve the desired power or greater. So what you basically do is solve this equation. You want to know the probability that z is greater than little z, I'll put critical here, the critical value based on your alpha level. You want it given that HA is true, so your specific effect size is true, and you want that to be greater than or equal to what we call power. So that's what you're solving. And if I just plug things in, let's assume we've got a one-sided test, and we want the critical value to be 0.05, and we're looking at alternatives that are greater than the null value. So our null would be, as usual, mu, the true mean, is equal to mu0, and the alternative in this case would be that mu is greater than or equal to mu0. But we'll even be more specific. We'll say it's equal to some mu a. So we have some value so that this difference between mu a and mu0 is significant, in not necessarily statistically, but is significant for the study. And that's how you choose the minimum difference, the effect size you wish to test. So the effect size would be defined as mu a minus mu0. If we're doing a one-sided test and we want the critical value, alpha, to be 0.05, that means the critical value, z crit, will be the 90th quantile of the standard normal, which is equal to 1.64 around. So one would plug these things back into here, and you'd get probability that x bar minus mu0 over sigma with the square root of n is greater than 1.64 4 would be greater than the power. So what do we choose as power? It's often shows as 80% or 90%. We'll just, I'll just choose for now 0.80. Now, without going into the details, which I'll do later, the sample size required is just solving this equation. So you can solve this for n, and when you do so, you get the what would be your sample size required if you had a critical alpha level of 0.05, a one-sided test, you wanted a power of 80% or greater, and you have to specify which you have to add into this equation. It's not there yet. The effect size you want, you have to have some estimate of the standard deviation of the original random variable. And when you plug all those unknowns in, you can get back your required sample size. And it's usually interpreted to be that size or bigger that you require. So, and there's lots of power sample size calculations in packages in R that you can use. Now we'll look at a specific example. So we'll assume that we know that the standard deviation of the random variable that we're taking the average for is 1. So, again, this means that is equal to sigma is equal to 1. Well, our null value will be 0. That's determined by the question and what's the nature of nothing happening, the null. We'll have a one-sided alternative that mu is bigger than 0, and then we'll set our alpha at the typical level at 0.05. So we only want, if the null is true, we only want to make a mistake in repeated experiments 5% of the time where we falsely reject the null. And so that's a compromise between never having a false rejection of a null, but still having some power in order to detect a real difference. We'll, in this case, choose our power to be 90%. So, and we want our effect size to be 0.8. So really, in this case, our mu A, the alternative, would be 0.8. So I'll call mu A 0.8, and I'll call this mu A, just to be consistent with the last slide. And it's our proposed alternative. It's what it's the, if we see a difference of the mean, which is 0, of 0.8 or greater, then we're interested in detected it statistically. That's what it means. So, our effect size is, again, defined to be mu A minus mu 0, which in this case is also just equal to mu A, since the null value is 0. And in this case, we want to figure out what sample size would need to achieve if all these things were true. And we wanted 90% power. So we wanted the probability of rejecting the null under our specified alternative, which is right here, to be 90% or greater. Now we could do this in a couple ways. I mentioned in earlier slides, you can actually derive a formula from that equation I wrote out, but you can sort of play around with these, with R, and come at the sample size required as well, and that's what's done here. So again, first of all, we'll look at the distribution of the sample average. So we want to look at the distribution of this under the null, and under the null it would be normal, mean 0, and standard deviation 1 over the square root of 10, right? Because that was our standard deviation, and that's our sample size. If we're assuming, let's start by assuming, of course, that n is 10, and see what our power would be. And so if we looked at a critical value, that is, I want to know, if I look at the null distribution of x bar itself, so under the null, under H0, it would be centered around 0. And then I want to find a value here so that there's only 5%. Because that means if I got an average in my data that was this big or bigger, this would be the z crit. Well, it wouldn't be the z crit because it's actually in the scale of the mean, but just say, I'll say x bar crit. Then I know when I converted everything to a z statistic and look at the standard normal, I would reject it. but this case, we'll just do this on the scale of the original average. So we won't standardize by dividing by the standard error. And so when I do that, I get 0.5201. So that would be the critical value as measured not on the test statistic, but not on the actual average that you get back from your data. And if you got a 0.52 or less, you would fail to reject the null hypothesis. So this value here is 0.52. And again, that's under the distribution being normal for the sample average. In this case, we'll just assume the original variable is normally distributed and that the null value is 0. So under that distribution, which is here for the average, then if we got greater than 0.52, we would reject the null hypothesis. So that gives us our critical value. Now what we need to do is, what is actually the power? What's the probability of having a value greater than that critical value under not the null, but the alternative? And so that's what this provides here. So this right here is the probability that x bar will be greater than x bar crit, based on the sample size of 10 in this case, right? And so that's what this gives, and that is essentially the power. This will equal the power, because that's the probability of us rejecting the null hypothesis if it's not true. The only thing we have to put in here is we have to put the new mean in. So we have to put in h, what I call mu a, which is our proposed alternative to the null, which was 0 in this case. So now I want the probability being greater than this value. That's why lower tail is false. If the distribution is a mean with 0.8, that would be our proposed alternative, and the same standard deviation of the mean, right? So again, this is the standard deviation of the x bar, and the mean doesn't affect that. The change in the mean, we're assuming the standard deviation stays the same. And when we do that, we get the power, and that is this quantity here. So that suggests that we're not quite at 90%. So we have to increase the sample size. It's greater than 80, so if your power you desired was 80 or greater, 10 is a good sample size for that. So let's keep on increasing in and see when, in fact, this probability gets beyond the value that we want, which is 0.9. But first, let's look at this diagram. So this just shows it. Here is the distribution. This is really the distribution of x bar under the null. That's what I have here. This is the distribution of the same quantity, x bar, but under the alternative. And then this is the critical. This provides the critical value, the x bar crit I put earlier, and the area to the right of that is the power. So this just does the exact same we did, but just in visual form. So we're repeating this for different sample sizes. We'll start with n equals 13. Again, that means that under the null, x bar will be distributed normal. Again, the mean was 0. That was our proposed null value. And then 1 over the square root of 13. And this is the null. Under alternative, x bar will be distributed as normal with mean 0.8. Same alternative value over the square root of 13. So we're going to use those two distributions, this one to get the critical value and this one to get the power. So that's what we do. The same thing we did last time. We change the n to 13. We get the critical value on the average scale, and that turns out to be, we don't even report it here, but it's some other value. Smaller, no doubt, because the variance goes down because the sample size goes up. And then we get the power now of that same mean under this new sample size, and we get 0.89. That's pretty darn close to 90, but typically you want to go just above, right? And you can only add discrete sample sizes. So you go up one more, repeat the exercise, get a new standard deviation of the average, a new critical value, get the probability being greater than that critical value under the alternative again, and it's 0.91. So you would go with 14 because it reaches the power that you want. And you want the power again to be, greater than or equal to the specified value. So what effect sample size required for hypothesis tests? Um, so the difference between the null and true values being the same, smaller p-values occur with larger n. So, n, of course, affects the power. We know that. Higher power requires larger n. So everything else being equal, if you have a fixed alternative to the mean that you want to look at the power for, the bigger the n is, the more power you'll have, keeping everything else the same. For given alpha, power for two-sided alternatives requires a larger n than one-sided. So I want 80% power. Then the two-sided test will require a larger sample size than a one-sided, again, because your rejection area is smaller. And then finally, if you want to detect smaller and smaller differences, so if I really want to detect small differences from the null value, then you require larger n. So this should be mu 0. So, and that makes sense. If you need more data to be able to distinguish smaller differences between the null value for the mean and the alternative value as they get smaller and smaller. So this is just adding some terminology. I've used this sometimes in lecture, but just to make it formal here, alpha is also known as the type 1 error rate. And again, type 1 error rate is the probability of rejecting H0 given H0 is true. And you want to make that small, of course. You can't make it 0, because if you make it 0, that means your power also will be 0. So you have to make it, you have to have some probability of error, and 5% seems to be the standard. So usually, again, this was equal to the alpha level, and it's usually 0.05. Power, well, power is 1 minus the type 2 error, and the type 2 error is just the other kind. So type 2 error is the probability of accepting, or I shouldn't say that, right? We never accept, we fail to reject. So fail to reject null when null false. And sometimes that's called beta. So power is just 1 minus beta, because it's the probability of actually rejecting the null if the null is false. And you can think of the results from one study. You get your test statistic, you have your critical value, and you reject or accept that. If H0 is true and you reject, that's a type 1 error. If it's true, if H1 is true and you reject, that's a good thing. That means that you have enough power to be able to reject the alternative hypothesis. It's H0 true and you fail to reject H0. Of course, that's 1 minus the type 1 error, and that's good. And then likewise, if you fail to reject H0 but it's not true, then that's a type 2 error. So this right here is power. This is beta. And then this right here would be 1 minus alpha. And that's testing for now. We'll go back to it as we get more complicated situations, like when we have to estimate the standard deviation. Test statistic can vary a little bit. Mainly the distribution of the test statistic changes, and we'll learn about that in upcoming lectures. But this gives basically the structure for doing hypothesis tests, confidence intervals, and finally how to use the construction of those to do sample size calculations.